Welcome to Csis 235 Object-Oriented Programming. This is Lecture 2 on Basic Object-Oriented Design. So let's take a quick look at some of the terms. One thing that you want to get familiar with is abstraction. And actually, computer science as a whole is a science of abstraction, that is creating the right model for a problem and devising the appropriate mechanizable techniques to solve it. That is, come up with the right way of looking at solving a problem and then set up, let's say, the classes and methods to solve that problem, or the algorithms, I guess you could say that. So our goal in this course as a whole is to learn some of the techniques used in writing really great software. That's what we want to do. And object-oriented design techniques can be used to write really great software. So right now, the way things look, object-oriented design is the best way of approaching a lot of problem-solving techniques. Let's take a quick look at the objectives for this chapter. After studying this chapter, you should understand the nature of software systems, what software systems are like, how abstraction and decomposition are used to deal with complexity in problems. And basically, we can say that's breaking up a big problem into smaller classes, and how to use abstraction. That is, how to just basically model a problem. We also want to understand the fundamental components of a program, that is data and functionality. Of course, you can think of this, roughly speaking, you can think of this as data members and methods, but it's also more abstract than that, but you can think of it that way. We also want to understand objects and object-oriented systems, that is, how to write code from an object-oriented perspective, and their relationship to software systems in general. Also, you want to be able to identify basic components in complex structures. If you have a big program, you want to figure out what the basic structures of such of big programs can be. So there's probably some part of the program that deals with files, or part of the program that deals with network communication, things like that. How are those things, how do they fit in with the rest of this complex program? You also want to be able to provide examples of abstraction levels from least abstract to more abstract. And actually, we don't, at the very beginning of this course, we don't really do a lot of abstract stuff. We sort of get into that later on. You want to be able to explain how composition and abstraction simplify the organization of a system, and provide informal algorithms for common activities. So this course is not a course about algorithms, but we will look at a few. So I'm hoping that you've seen maybe a little bit of searching, and it can be just even simply scanning an array for a number, something like that. That's a valid way of searching. Hoping that maybe you have heard of the word sorting. That is, how do you get an array of numbers and get them in increasing order, things like that. Maybe some of you have seen a sorting method, but we will see a little bit of that. So we will look at some formal algorithms and informal algorithms. Okay, so let's move on. Let's take a look at the nature of software systems. So what is software? Software is a temporary solution to a changing problem. So if you're whatever it is, the problem might be accounting, might be managing logistics for a company, or tracking packages, whatever it is. Typically, you will have a software system that works for a while, and then you might find that your needs are changing, and you might need a different system. Even when you have a software system in place, often they will change. So they are dynamic and they are complex. Software systems, if they were simple, I guess there wouldn't be so much demand for computer scientists in general. Okay, so dealing with complexity. So there is most software programs are complex, but you can decompose them and you can use abstraction to help you solve problems. So typically software systems are large and must be broken down into manageable pieces, and usually you have teams working on some of the pieces and they come back together and deal with a composite structure, put these separate packages into one single software package. With software, you have parts that must interact together. Certainly in this course, we will deal with this. We'll have classes that interact with each other, and you want to find out the best way to have these classes interact. The more parts, the more interaction. So I'm hoping by the end of this course, you will have set up programs with 10, maybe more classes. So the more parts, usually the more interaction. Maybe, but sometimes we can manage that complexity and minimize the interaction. System complexity is proportional to the number of parts, so we have to find ways to tame that complexity. So two of the things that we can use are composition and abstraction. Composition is the process of building a system using simpler parts or components. Right now we're just setting up simple classes that have as data members maybe an int and a double or an integer, things like that. And later on we'll get into using classes where each data member could be a class, which itself will contain many data members. So this is something that we'll keep building on through the rest of the semester. We'll build up a system using simpler parts or components. The other part of dealing with complexity is abstraction. That is, deal with system components without worrying about the details of how components are constructed. So basically this looks like is you imagine a system as a black box. So you know what maybe goes in, what comes out, but you ignore the details. So abstraction is sort of like that. It's the process of ignoring some of the details. It's often some of these details are not relevant to the problem at hand. And you want to emphasize just the essential details. Okay, so that's something that we'll keep dealing with for the rest of this semester. Two aspects of a system, as we talked about very briefly. There's data and functionality. Data is information that the program deals with. Often in a simple class, this might just be data members. So that's information. So data descriptions are fixed, and individual data values change each time the program runs. So for example, if you're dealing with a game, let's say, the score can be a data value, and that might change. The number of points that you get for each activity or something might change, and so those are all things that can change every time the program runs. Other aspect of a system, functionality. What does the program do with data? You can think of this, roughly speaking, as methods, but in more abstract terms, it's some kind of computation. And what is computation? It's just a goal-directed sequence of actions performed by a processor. So you can also think of it as a series of things that you try to do in a method, let's say. And it's very closely related to algorithms. So you might have seen The Social Network. It's the story of Mark Zuckerberg and Facebook. And they have a scene where Mark Zuckerberg is asking Eduardo Saverin, I want the algorithm, give me the algorithm. And Eduardo Saverin, I don't know if you remember this, but he writes a simple formula. It's pretty simple. That, technically speaking, is not an algorithm. Maybe it can be loosely considered an algorithm, but it was more of a computation. It's just a sequence of actions that can be implemented in code pretty straightforwardly. Algorithms usually are a little bit more complicated. You can define it as a set of instructions describing a pattern of behavior guaranteed to achieve a goal. And there are some technical definitions. Usually an algorithm should technically be something that will stop. So nothing with an infinite loop can be considered an algorithm. Okay. So with all of these, there have been many ways of approaching software. And right now, the object-oriented approach to solving problems has been the one that's been working the best. So right now, even though you can use non-object-oriented programming languages like C, or maybe some JavaScript that's not object-oriented, or PHP, it turns out for most big problems, all right, you have to use an object-oriented technique of some kind. So it's usually C++, C#, Java, and maybe object-oriented Python, and other languages like that seem to be working the best. And if you're working for a company these days, you just have to know what object-oriented approaches are for solving problems. Okay, so these object-oriented systems are intended to produce systems that are composite, modular, built using abstraction, and organized around data. And data is basically king right now. It's everything. All programs are based on data. And what you will do is, if you work in a company, you will have systems that are composed of many pieces, and usually you'll have teams working on each piece. And each of these pieces are modular, so that you can have these things put together to solve a single program usually. Okay, so objects are abstractions used to describe the problem. So for example, in this, we'll look at very simple objects. For example, one of the first things we look at is the counter class. All it does is count. Just keeps count. That's it. You increment the counter, you reset the counter. That's very simple things like that. If you have an accounting system, let's say, you would have to keep track of accounts. And if you're working for a bank, you'd have an account class that would keep track of everything that had to deal with a single account, and so on. And if you had to deal with people, you'd have a person class, which would have things like a name, address, some kind of ID, maybe age, things like that, date of birth, things like that. So the idea is just that you create classes that mirror the real world situation that you're trying to solve. So if you deal with people, you have to have a person class pretty much. Okay, the functionality of the whole program is distributed to these objects. So you put a whole bunch of these objects together to solve a single program. Each object may have algorithms to accomplish specific tasks, or I guess this should really say methods. Each object should have methods to accomplish specific tasks. Okay, so let's just summarize here. Software systems are complex, and these systems change over time. To address these difficulties, we make extensive use of abstraction. We'll use this for the rest of the semester. And we'll build systems that are modular and composite. That's our aim, to build these nice object-oriented systems that can be taken apart, fixed separately, and put back together. Okay, so that's really what I wanted to talk about today. Definitely, if you have questions, just let me know. Next up, we'll look at Chapter 1 in Nino. And before the next class, try out some of the example code from Chapter 1 Nino using Eclipse.